What I'm going to talk about is this very interesting perspective on functional programming that I developed while writing a book on it. So first, my background, I used to write academic papers with lots of formulas and diagrams that looks like this. But in 2010, I repented and turned to software engineering. Functional programming attracted my attention around 2008, as far as I remember, with programming languages such as OCaml, Haskell, and a bit later Scala. I was learning from papers, books, online tutorials, and especially meetups in San Francisco where I worked. I've been attending the Scale by the Bay conference since 2014, and I'm using Scala at my job since 2015. While I was attending various meetups, I found that the functional programming community is very much unlike other communities of programmers like Java, Python, and so on, because those other communities focused on designing and using libraries, frameworks, and they talk like, let's override this method, use this annotation, make this config, let's call this function, and so on. So quite typical for programming. While the functional programming community talks in a very different way. They talk like referential transparency and algebraic data types and monoid laws and so on. Actually, John DeGoes has, oops, should have done it. So this is not. John DeGoes made a glossary, I'm showing the link here, of functional programming terminology with more than 100 terms of this kind. And this is not just some graduate students showing off. These are programmers. They're using these things for programming. From the Scale by the Bay conference in 2018, one of the talks was called the functor replicative monad talk. And this means, note this title, the functor replicative monad talk. It means everyone expects to hear these concepts mentioned. And so this is a kind of a standard and accepted part of functional programming community that you talk about those things. Here's an example of an actual Scala error message. Found one thing and required something else where this type, blah, 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 is a GADT's column. Now, this is quite interesting. So why do they talk like this? And to do functional programming, should I learn all of this? Like, for example, catamorphisms. What else do I have to learn? Are there logomorphisms or only catamorphisms? And how do I learn about this? So these were my questions. My main questions were, which is the theoretical knowledge? Because this looks obviously like some math, some knowledge of mathematics or something like this. So which of this knowledge actually will help me write Scala code? Now, it's not like I cannot learn a lot of new things, but do I have to? I have my life, not so much time. I don't want to spend time learning about something that will not help me. And where can I learn it? What are the books or tutorials or something? Where can I find this? The material that will allow me to learn this. So the questions that I had, for instance, I started learning this. Well, what do the monad laws ensure? Why are they imposed? How do I verify that those laws hold? When is a data structure a functor, a monad, or applicative? So there is this talk about functor, monad, and applicative, but it doesn't answer those questions. I kept reading, and those materials gave me more answers than questions, more questions than answers. For instance, a lot of materials, a lot of books have heuristic explanations without derivations and without proofs. Here's an example, a recently published book, The Book of Monads, which I looked forward to. it's a very good and interesting book, but it does not actually prove the monad laws for any of the monads. It shows you the laws, but it never proves them. So for instance, if you know there is a monad such as a state monad or continuation monad or some other such monad, but so it shows those monads and how to code them, but it doesn't prove that they satisfy the laws of the monads. And to me, this was a first question. So is this correct? How do I know that? And a few books, like, for example, the Haskell wiki books, or these books, the Introduction to Programming with Haskell and Functional Programming in Scala, they show some proofs, but only simple ones. And that actually creates a false impression that all proofs are simple. And to me, this is a red flag. Other papers that I found were far too abstract, far too academic. Pure theory for the sake of theory with no applications in programming. And I don't want that. I'm not interested in this. I've spent a lot of time in my life doing academic theory with no applications. So now I would like to have a cut at some point. I want to decrease the scope of theory that needs to be learned. So here are examples of pure theory with no applications. Now, this is a joke in the functional programming community that monads are just monoids in the category of end-effectors. What's the problem? Obviously, this phrase doesn't explain anything, and there are lots of problems with understanding monads that this doesn't help you to understand. And if you understand why this is true, so you study enough category theory to understand why this is true, this will help you not at all in using monads, in implementing monads. For example, if you have a data structure in your code that you want to make into a monad, it will not help you at all to know this thing. So this is, in my view, an example of purely academic knowledge that I would like to avoid. Or another example, this is from Wikipedia. Any monad comes from an explicit adjunction of some functors. Well, great. At some point, I thought this was a very important theoretical result that will help me do something like monad transformers. But no, actually, I went through a lot of calculations and I found zero use of this information. So this is what motivated me to write a book. I want to show the correct scope of theory that is necessary, that is helpful, and I want to avoid theory that is not helpful. So the only way to do this is to derive all results from scratch and motivate everything. So you have to, before you say monad has to satisfy monad laws, you have to motivate why these laws are necessary. What if you don't satisfy them? Is your program going to crash or what? You have to show that, something like this. And another thing I found is that just by chance, I found that there is a way to organize systematically all this theory, all this practice relevant part of functional programming theory can be organized in a way that is quite systematic. And at the same time, it tells you what is not necessary and what is necessary. So I will tell you how this is. So this book I'm writing is called The Science of Functional Programming. It talks about theory of applications of functional programming in a theoretical way, but it is focused on that part of theory which is useful for practice. It gives you the techniques for deriving and verifying the properties of code, and gives you practical motivations for everything. So 12.5 out of 14 chapters of this book are ready. I'm working this book in my spare time, which means slowly, but it's pretty much almost done. It should be done next year. So now, the first thing that struck me when I got into functional programming is that in functional programming, there are certain questions about code that can be answered rigorously, not a matter of opinion, but a matter of mathematical derivation and reasoning. And these answers are directly helpful when you write the code, when you design the types that your application is using. That's where those answers help you. So this is quite unusual because in other paradigms, you don't have, like an object-oriented program, you don't have this. Here are examples of questions that are that have unambiguous answers. Suppose you are given a value of type either z of r to a, or you're given the value of type r to either z of a. Can you compute the value of the other type? So a, r, and z are type parameters, so arbitrary unknown types. So I can think of two functions. One, the function f that goes from one type to the other, and the function g that goes from either of this into this. Can I implement these functions? Turns out that you can implement g, and pretty much in only one way. So the code of g is like this, but f cannot be implemented. And it is not because we are not clever enough, that we don't know some tricks of Scala or functional programming, that we're not able to implement f. It's because it's mathematically impossible to implement f. Now, this is quite amazing in some sense. How can it be that it's mathematically impossible to implement a function with a certain type signature? This doesn't happen in other programming paradigms. So programmers need to develop intuition about why this is so. The theory behind these results about being able to implement or not is called the Curry-Howard isomorphism. And there is the LJT algorithm, so-called, that allows you to develop code automatically. So you can derive or generate code for the function g automatically, just from the type signature. At the same time, this algorithm will tell you that the function f cannot be implemented, and that's rigorous. Second example, I want to combine future and either together. How do I combine them? Well, I need to write code like this. Maybe I have a future, I have an either. This, of course, won't compile. So what do I do? How do I combine either and future? Do I combine them like this, or I combine them like this? And I want to implement flat map for this type so that I can write a for yield block. It turns out that this is wrong and this is correct. This is rigorous. Programmers need to develop intuition about why this is so. They don't have to test this or prove themselves, but there is a theory behind it which actually proves that this is true. And this is a theory of monad transformers and their laws. Third example, suppose you have this data structure. Can you implement flat map for it? It will be this type signature, just a standard type signature of flat map. Turns out that you can implement this type signature, but it will always fail the monad laws. Whatever you implement, you also implement pure for this data type, and it will always fail the monad laws. Now, programmers need to develop intuition about it. How do you modify this? What is wrong with this type? How do you, what else does it need in order to be able to have a monad instance? For example, this, if you just change the option into an either, it's a very small change, this becomes a lawful monad. This is not obvious at all. I'm not trying to say that this is obvious. And finding this requires quite a bit of work, but I already have done this work and I have written it all up. So you don't have to test this. You can look it up in my book. And in principle, you could study the theory as well. It's all explained and derived. So the result is that the functional programming paradigm is similar in some ways to engineering. And that was another realization that hit me at some point. Why is it so different? It's because it's not like other programming paradigms that are similar to artisanship, trades and crafts. In artisanship, people work according to theory, and not to theory, to tradition, to experience. They learn by doing, and that's how most programmers learn. In functional programming, there is theory that you can study, and this theory gives you rigorous answers to certain questions relevant to your design. And this is exactly the situation in engineering. Some engineering knowledge is based on rigorous science. Of course, not all. Some engineering knowledge is not science, it is tradition and experience, but a lot of it is based on science. And in this way, you can see functional programming is also based on science. My book is an attempt to figure out what that science is. What is the scope? I'm not inventing anything new. I'm figuring out what is the scope of these theories that a functional programmer could study in order to answer the questions they have. Another similarity between engineering and functional programming is that engineers use special terminology, just like functional programmers do. Here are examples. Rank for tensors. Yeah, functional programmers use rank in types. I'm not saying that they're similar, not similar in any way, but this is a kind of special terminology. We have Fourier transform, we have delta function, and in functional programming, you have lambda functions, or here you have Gibbs free energy. I'm showing links where these terms are being used in engineering presentations or books. And here are where these terms are being used in functional programming presentations or discussions. So for example, Gibbs free energy, and you have free monads. The word free does not have the usual meaning here. It's terminology. It is not self-explanatory. You have to learn what this means in every case. Finally, it turns out that the main system behind functional programming is the map filter reduce. And if you just look at map filter reduce, and if you study that, you will be forced into doing all of what I did, all of what I was telling you before, and more. So what is map filter reduce? Well, we know that it is a very powerful method of programming where you write iterations without loops, and you generalize from there. So you have certain functions that operate on entire data sets and produce new entire data sets, at least conceptually. And implementations of these could be very different. For example, some of them could work with clusters, parallel processing, or even relational databases, and so on. The map filter reduce programming style is a success story of functional programming. And it forces you to use nameless functions like these. It forces you to find out what the essential methods are, and they are map, filter, flat map, zip, and fold. The natural question is, what are the data types that support these methods? These are, for example, the algebraic data types that you're talking about, trees, or, for example, a perfect shaped tree that always has to be perfectly balanced like this. Which methods can I define for this data type? Can I define, like, for this data type, say? Let's say this is my business logic. Can I define map for it, filter, flat map, zip, fold? It turns out that you can define some of these methods, but not all, for certain data types. And that gives me a systematic approach to describing and understanding functional programming. You determine the required laws of map, filter, flat map, zip, and fold. These laws express the programmer's expectations about what these methods should do. So you motivate them, you write them down, you define the corresponding type classes, And then you find all the type constructions that preserve type class laws. Here are some examples of these type constructions that I'm talking about. If P and Q are filterable functors, then so is either P of A, Q of A. So that is also a filterable functor. So filterable is something that has a filter function. If P of A is a monad, then either A of P of A is also a monad. If P and A and Q and A are monads, then the pair is a monad. If P of A is a contravariant functor, then this function type is a monad. If these two are applicative, then either P and the pair of A, Q of A is applicative. Now, it's not just a pair of P and Q. That's not true. It is not necessarily applicative, but this does work. So I found many more constructions of this sort, and sometimes when I found what type constructions are necessary, I had to define new type classes, such as contravariant functor or contravariant filterable, contravariant applicative, necessary to find out what are the possible data types that have these properties. And that is my system, essentially, in one slide. So this is the systematic approach to determining what is a practically relevant theory. This is obviously the practically relevant functional programming style. What are its theoretical properties so that I can describe all possible data types that can have those methods. This helps me develop intuition about how to implement these methods, what data types can and cannot have those methods, and how to check, how to prove the laws. Another thing that I realized while doing this is that types play a central role in functional programming as it is practiced today. It's not just programming with functions. It is not just immutable values and functions. That maybe was 40 years ago when they only had Lisp. Today, types play a central role, and not just that they are checked at compile time, although that's important, but that specific types are being used. So functional programming today is programming with functions, with map reduce, filter, and with specific kinds of types. And I can list what types those are. Unit types, generics or type parameters, product types, coproduct or disjunctive union, function types, and recursive types, which are defined in Scala maybe like this. It's not necessarily practical, but theoretically, for any recursion scheme, you have a recursive type. So given just these 6 type constructions, I can do pretty much all of functional programming that as practiced today. I can then enumerate all possible type classes, like all possible functors, monads, applicatives, traversables, filterables, that are made up of these types and type constructions. And in some cases, I can automatically generate type class instances for them. Another little detail is that these types correspond to logical propositions. For example, coproduct corresponds to A or B, product corresponds to A to B, and so on. And not all programming languages support these. So if a programming language doesn't support, say, coproducts, it means that the logic of its types is incomplete, and you cannot express certain things in the types. And it turns out this is practically relevant. It's important that a programming language should support coproducts and pattern matching on them. Languages that don't support coproducts, like the Go language, where they decided not to support coproducts, will make you suffer. They will write code that will be a lot of boilerplate, error prone, and you will not be able to rewrite it or refactor it in any way. Whereas in Scala, you would return try or either in order to return error or result. And the error here, the design error in the programming language, is that instead of returning a disjunction, they return a conjunction. So instead of returning A or B, they return A and B. It's just a logical mistake in the design of the language. don't do this. Finally, in the little remaining time, do we have a chat question in this Zoom, or is it something that I can go over later?
There are no questions yet.
Okay, I see something in the Zoom chat. Okay, so I have 5 minutes left, or 4. Let me just go very quickly over little things that I found, the surprises. The thing is, when you go from scratch and derive everything, then you're bound to find things that you didn't expect, because science is unforgiving. It doesn't know what you expected. It has its own logic. There are many things that I believed to be true, and I tried to prove them, and I couldn't because they were incorrect. And there were other things that I didn't think were true, but turned out to be true. So let me just go very quickly over those surprises. There are too many of them, actually. Each chapter gave me at least one surprise when I went through it. For example, there's a perfect shape tree type like this, and you can define a type in Scala where you can only have perfect shaped trees. The usual tree allows you to have different branchings at different places. This type does not, and you can define it via recursive algebraic data type, which I didn't expect you could, but yes, you could. It's not obvious, but you can do this. I'll skip other things. A fun thing I found is that type inference exists, which is determining type signature from given code, but there's also code inference, determining code from given type signature. I already touched upon it. I was able to implement this LGT algorithm as a library in Scala. And then I can write code like this. I write a type signature and say equals implement. And there is a macro here, which will find the necessary code and compile it. And then I can use it right away. And this can do a type signature like this, which is artificial and quite complicated, not obvious. And if the type signature cannot be implemented, it tells you. Another funny thing I found is that when I write proofs, I would like to write proofs in a shorter notation, not in code. And I found that matrices can be used to represent algebraic data types, coproducts. So functions from a coproduct to coproduct can be written very well as a matrix. And you can write the types as rows and columns, rows for type of input and columns for type of output. And you put functions in there. It's a very terse notation that allows you to use matrices for proofs. Very nice notation, where you can use matrix multiplication rules for function composition. Very interesting, unusual thing that I found, but helped save me time. Filterable functors is a neglected type class, not usually described, but it's an important one. Another thing I found is that certain data types just cannot be monads. Well, it's not obvious why. I don't think anybody really knows the deep reason why. Anyway, but the programmer needs to understand that this is not always possible to have a monad. Breadth first traversal of trees. So you can define special versions of fold and traverse that do breadth first traversal. Free type classes. So there's free applicative, free functor, but there is no free foldable or free traversable. Interesting, isn't it? But the programmer needs to know this, how to define free type classes. Another funny thing I found, tagless final is just a church encoding of the free monad. What is the problem? Well, another joke, of course. Church encoding is a pretty difficult thing to prove that it works correctly. So I have to go through quite a lot of work to prove it. Monad transformers are just pointed end effectors in the category of monads. I'll stop here. Functional programming does have a steep learning curve because it is engineering. Engineering means you have to learn some theory, some science, and then you can design much more complicated machinery. Without science, You can design good working machinery, but not too complicated. That's the whole difference between engineering and artisanship. Doesn't mean that artisanship is bad, it's just not as powerful. At the same time, you can benefit already from the simplest techniques, like map, filter, reduce, ADTs for yield, and you can stop there, you will reap the low-hanging fruit. My book is free on the web with full source code, and it will be hopefully finished next year. Thank you very much.